Okay, welcome back to our unit here on nuclear chemistry. Today's topic is half-life and nuclear energy. Lesson 3 of 3, your objectives are as follows. You'll learn what half-life is. Okay, you will understand radioactive dating and how scientists use half-life to estimate the age of an object. Okay, you will understand the process of nuclear fission and nuclear fusion and how they produce energy. Okay, for your quick write, feel free to pause this video anytime you feel necessary. Okay, let's say you have $100 and you can only spend half of what you have every day. How much money would you have left after 2 days or 3 days? Okay, imagine you have 100 pennies in a box and all of them are facing heads up. Okay, if you shook that box for 20 seconds, how many do you think would be heads? How many do you think would be tails? Okay, how do you think energy is produced in nuclear power plants? How do you think the sun produces energy? Okay, go ahead and pause this while you do your quick write. I'm going to move on. All right, so half-life. Half-life is the length of time it takes an amount of a radioactive element to decay to half of the original amount. Okay, so think about what that means. The decay process is constant and does not stop. Recall that radioactive decay occurs when an unstable atom or isotope for an element emits radiation, alpha, beta, gamma radiation, to form a more stable isotope or atom. Okay, the unstable isotope is called the parent material and will decay into the stable isotope produced, which is called the daughter material. Okay. Recall that unstable carbon-14 will decay into stable nitrogen-14 through beta decay. Carbon-14 is the unstable parent material. Nitrogen-14 is what we call the stable daughter material. Carbon-14 has a half-life of 5,730 years. Okay? So let's say we start with 100% of unstable carbon-14 here. And we know it's going to turn into nitrogen-14 here. Okay? We're at 0 half-lives. Okay? After one half-life, 5,730 years go by, half of the unstable carbon-14 atoms or isotopes will have decayed into stable nitrogen-14 atoms or isotopes. Okay, so this leaves us with 50% nitrogen-14 and 50% of carbon-14 after one half-life, or 5,730 years. So we have half of what we originally had. Okay. After 2 half-lives, or another 5,730 years, carbon-14 will continue to decay into stable nitrogen-14, the daughter product. Okay. So after a total of 11,460 years, or 2 half-lives, we're left with 25% carbon-14 and 75% nitrogen-14. All right. So you can see that almost all of our original carbon-14 is almost gone after 2 half-lives. Only 25% remains. And notice 50% is half of 100%. 25% is half of 50%. Okay? Or, okay, we have 0, 1, 2 half-lives have gone by. All right? So for your notes, what is half-life? Question on the left-hand side. Okay, answer on the right-hand side. Please draw this simple diagram for your notes. I'm going to move on. All right, so practice. Try to determine the percentage of carbon-14 and nitrogen-14 that will be left in a fossilized bone after, okay, 5,730 years, okay, 11,580 years, and 17,310 years, okay? So go ahead and pause this while you work on these. When you're ready to see the answers, hit play. Okay, let's see how you did. Okay, so after one half-life, 5,730 years, okay, 50-50, right? 50-50. Now, after 2 half-lives, or 11,580 years, okay, 25% carbon-14, 75% nitrogen-14. Okay, and after 17,310 years, we have 12.5% carbon-14 and 87.5% nitrogen-14. Okay, hopefully you did pretty good on those. All right, so calculating half-life. Let's say a fossil contains 16 grams of carbon-14. If its half-life is 5,730 years, what is the mass of carbon-14 remaining after 3 half-lives? Okay, well, one way to solve this problem is to set up a table. Okay, 0 half-lives, we have 16 grams. 1 half-life, 8 grams, half of 16. 2 half-lives, 4 grams. 3 half-lives, 2 grams. Okay, so we can see that after 3 half-lives, all right, 2 grams of carbon-14 remains. There's our answer. Okay, so what is the mass of carbon-14 remaining after 3 half-lives? 2 grams. So we just established this. There's another way to do this though. Okay, another way we can solve this is by using the equation below, where n is the number of half-lives, m subscript I is the initial or starting mass, and m subscript f is the final or remaining mass. All right, with this equation. So, okay, substituting our values in, we get 16 is what we started with. Okay, well, what's the half-life? How many half-lives have gone by? Okay. Okay, 3. So after that, it just solve for m subscript f. We get 2 grams. Okay, so the same answer we had in our table over here. Okay, so that's calculating half-life. All right, so go ahead and practice. All right, go ahead and pause this while you work on this. Hit play when you're ready to see the answer. Okay, let's see how you did. If a fossil contains 20 grams of carbon-14 in it, how much carbon-14 in grams will remain after 1 half-life here? Okay, we get 10 grams. And then for 2 half-lives, well, what's half of 10? Okay, 5 grams. And after 3 half-lives, well, what's half of 5? Okay, 2.5 grams. Hopefully you did pretty good on those. All right, so half-life and radioactive dating. Using half-life, we can date an object's age, how old it is. Radioactive dating, also called radiometric dating, is the determination of the age of an object, usually an artifact, bone, rock, etc., based on the half-life, the rate of decay, and the amount of unstable radioactive isotope present in that object. Okay, so let's consider a scenario or problem here. Suppose an archaeologist finds a caveman's fire, okay, and he wants to know exactly how old a piece of charcoal, which is made up of carbon atoms, is from the caveman's fire. He wants to essentially know how old is this caveman's fire based on the age of a piece of charcoal. Okay. Well, the charcoal is found to have 12.5% carbon-14 and 87.5% nitrogen. Okay, so remember those two numbers there, 12.5% carbon-14 and 87.5% nitrogen. Okay, so we can solve this problem by using the half-life of carbon-14. Carbon-14 will decay into stable nitrogen-14 through beta decay. Okay, so suppose this piece of charcoal here contains 100 stable atoms over here. So these 100 atoms are in our piece of charcoal, okay, of carbon-14 unstable atoms here. This represents 100% of our sample. Okay, so the half-life of carbon-14 is 5,730 years. All right, so we're going to put this on the clock over here. Okay, so after 5,730 years here, all right, 1 half-life has gone by, and you can see that we're left with 50% carbon-14 and 50% nitrogen-14. All right, but our sample of charcoal contained 12.5% carbon-14 and 87.5% nitrogen-14. Okay, so it must be older. So let's see what happens after another half-life, 2 half-lives, or another 5,730 years. Okay, so you can see here, after another 5,730 years goes by, 2 half-lives, okay, we're left with 25% carbon-14 and 75% nitrogen-14. But remember, once again, our sample of charcoal contained 12.5% carbon-14 and 87.5% nitrogen-14. Okay, so let's see what happens after yet another 5,730 years, or 3 half-lives go by. Okay, so after 3 half-lives here, all right, we are left with 12.5% carbon-14 and 87.5% nitrogen-14. All right? Well, notice this is the same amount of carbon-14 and nitrogen-14 contained in our piece of charcoal. By comparing the amount of carbon-14 to the amount of nitrogen, we know that 3 half-lives have gone by. Okay? Therefore, the age of the piece of charcoal in caveman's fire is equal to 3 half-lives, right? 1, 2, 3. So 5,730 plus 5,730 plus 5,730, which gives us an age of the fire in the piece of charcoal, 17,190 years old. Okay? So, to clarify this point, we can graph the rate of decay of carbon-14 and still arrive at the same result. All right? So notice down here we have half-lives, and over here we have the amount of parent material in percent. Okay? Unstable carbon-14 atoms and stable nitrogen-14 atoms. All right? So let's start with 100% here of unstable carbon-14. All right? After 5,730 years goes by, 1 half-life, right? We have 50% unstable carbon-14 and 50% stable nitrogen-14. Okay, well, let's see what happens after another half-life. Okay, another 5,730 years goes by. Okay, the carbon atoms decay here into nitrogen-14, and we're left with 25% unstable carbon-14 and 75% stable nitrogen-14. Okay. So another 5,730 years goes by. Okay, 3 half-lives, right? And, okay, we have 12.5% unstable carbon-14 and 87.5% stable nitrogen-14. So if a piece of charcoal from a caveman fire contains 12.5% unstable carbon-14 and 87.5% stable nitrogen-14, then we know 3 half-lives have gone by. All right? 1 half-life is equal to 5,730 years. So after 3 half-lives, we can calculate the age of the fire. It becomes a simple addition problem. 5,730 plus 5,730 plus 5,730 gives us an age of the piece of charcoal in fire at 17,190 years. Okay, one thing to note. Okay, isotopes with short half-lives can be used to date more recent, younger objects. Okay, because carbon-14 has a half-life of 5,730 years, we use it to date younger things, such as early artifacts or pottery or young fossils. Okay, but isotopes with very long half-lives, like thorium-230 or uranium-238 down here, okay, they can be used to date extremely old objects. All right. So, for example, uranium-238 has a half-life of about 4.5 billion years, okay, and can be used to date the age of the Earth. Something very old, right? So, for your notes, what is radioactive decay? Question on the left-hand side. Okay, answer goes on the right-hand side. Go ahead and pause this while you write. Okay, I'm going to move on. All right, so go ahead and practice here. Okay, hit the pause button while you work on these 3 questions. When you're ready to see the answers, hit play. All right, so answer number 1. The rock fossil sample is 50,000 years old after 1 half-life. Okay, the rock fossil sample is 100,000 years old after 2 half-lives. And number 3, the rock fossil sample is 150,000 years old, or 3 half-lives have gone by. All right, so nuclear fission. Scientists discovered that the mass of a nucleus is slightly less than the sum of the masses of its protons and neutrons. For example, consider the table here below. Okay, notice the mass of 8 protons and 8 neutrons and the difference here. Okay, 8 protons and 8 neutrons has a mass of 2.67804 times 10 to the negative 24th grams, while a mass of an oxygen-16 nucleus, which contains 8 protons and 8 neutrons, weighs slightly less, 2.65535 times 10 to the negative 24th grams. Okay, so it weighs slightly less. Well, this difference in mass is called the mass defect, seen down below. Okay, So this difference is called the mass defect and helps hold the nucleus together. Okay, during nuclear fission, the mass is converted into energy through Einstein's famous equation E equals mc squared. During nuclear fission, a large nucleus is split or broken into two or more new nucleuses or nuclei, and mass is converted into energy. Because mass is destroyed, the law of conservation of matter does not hold true. Some matter is destroyed and a great deal is converted into energy. Many power plants throughout the world use nuclear fission to produce energy. Okay, so a common nuclear fission reaction involves the uranium-235 isotope below. Okay. In this reaction, uranium-235 is bombarded with a neutron to become unstable uranium-236, so it's now unstable. As a result of this instability, the uranium-236 nucleus releases a tremendous amount of energy. Okay? As energy is released, okay, the uranium-236 nucleus splits into two. The splitting of uranium-236 produces a krypton-92 nucleus and a barium-141 nucleus. 3 neutrons are also produced, causing a chain reaction as they collide with other uranium-235 atoms. Okay? The overall fission reaction can be summarized as follows. Okay, seen here. Okay, neutron plus uranium-235 makes barium-141 and krypton-92 and 3 neutrons. Okay? Well, this is a pretty cool thing, the chain reaction. So, the chain reaction begins with a single neutron. A neutron collides. Okay, notice the neutrons released in the initial reaction go on to collide with more uranium-235 isotopes and produce a sustainable chain reaction and unleashing a lot of energy. Okay, so for your notes, what is nuclear fission? Question on the left-hand side, answer on the right-hand side. I'm going to move on here. All right, so nuclear fusion. Fusion, unlike fission, is the combining of smaller atoms to form a larger one. Right now, our sun is harnessing nuclear fusion in its core to produce light and energy. It is only at the core or heart of our sun where extreme temperatures and pressures exist. And it is here where hydrogen atoms or isotopes are smashed, or we say fused together, releasing a large quantity of energy. Fusion is extremely important. Okay? It is the energy from the sun that supports all living things here on Earth. Humans are interested in harnessing the power of nuclear fusion here on Earth because it could become a clean, reliable source of energy that does not produce hazardous nuclear waste like fission reactions. Well, let's investigate the hydrogen fusion process a little more. Okay, hydrogen has 3 isotopes. We have protium, which is a single proton. Most of hydrogen is this, protium. But there's hydrogen 2, deuterium, which has a neutron and a proton. And there's hydrogen 3, which has 2 neutrons and 1 proton. It's very rare. One of the most common fusion reaction occurs when hydrogen 2, deuterium, fuses and combines with hydrogen 3. All right? The combination of these 2 isotopes releases a tremendous amount of energy and in the process creates a new element, helium, and a single neutron. So a common fusion reaction occurs when hydrogen 2 combines with hydrogen 3, tritium. Okay? The combining of these 2 isotopes releases a tremendous amount of energy, and at the same time, a helium nucleus, okay, is produced, a new element, and a single neutron is released, summarized by the reaction down here below. Okay? Deuterium plus tritium, 2 isotopes of hydrogen, release energy, helium, and a single neutron is given off. Okay, so for your notes, what is nuclear fusion? Question on the left-hand side, answer on the right-hand side. Okay, go ahead and pause this. I'm going to move on. Okay, so summarize. Okay, go ahead and pause this while you work on your summary, and we'll see you next time.